Hello, in this video I'm going to explain Faraday's law of induction. Um, Essentially, I'm going to go over the quick formula, and the formula is the EMF is equal to the change in magnetic flux divided by the change in time, and this is the negative. The reason it's negative is because there are electrons moving. I'll explain in a second. So if we have, essentially what it's saying is if we have a magnet, south, north, we're going to have a bunch of magnetic field lines going through this circle, this loop right here. Now if we're just leaving it there, there's going to be no change in magnetic flux. So if there'll be zero EMF created. If we decide to move this in, we will have a positive change in flux because we'll have more field lines that are currently missing it get moved in, so then they'll be inside. So you'll have a positive flux, a positive change in flux, and you'll get a current being produced in this direction. This is because, if you think about it, we have an increase in magnetic flux this way, this direction. If we then use the right hand rule, that'll be our thumb, and we'll have the electrons moving this direction. But because current flows in the opposite direction of the electron motion, because electrons are negative and current is the direction of positive motion, we flip it, hence the negative, and we get the current going this way. Similarly, if we have this north-south magnet and we are pulling out of the loop, we'll be then reducing the amount of magnetic flux in the loop. That being said, we will get a negative change in current and a negative change in flux, which will give us current in the opposite direction of the previous example. Again, because of this reasoning right here. If you just have a stationary magnet, try to guess what will happen. There'll be no change in flux. Change in flux. So that it just crossed out, and there's no EMF created. Now EMF is a difference of potential, and this is called, when we're moving a magnet and create a current and to create an EMF, it's called the induced current and the induced EMF. Basically, the basic idea behind all of this is that when you take a loop of some kind and stick it into a magnetic field, you're going to have some change in EMF if the flux is changing, or if there's more field or less field lines running through it, there'll be a change in EMF. Another way we can write this formula is the EMF is equal to the negative derivative time magnetic field times the area times the cosine theta between them. Now, if you don't understand this formula, it's in a previous video. And essentially what it's saying is this right here is the magnetic flux. So this is just another way of denoting it, so you might be able to understand it. I find these examples to be pretty simple, considering it's just slight changes in the, not slight, but I guess there's like, it's just changing the magnetic field lines, and you're going to induce a current in the loop. If you think about it, that makes sense, because loops create current, or create a magnetic field, if there's a current running through them. And it makes sense that if there's a magnetic field changing inside of them, there's a change in magnetic field, there's going to be a change in current. This only happens, obviously, if the magnetic flux is changing. So if you want to think about it another way, when you're lifting an object, you're adding potential energy to it. So go ahead and lift your notebook or your pencil sitting around you, your cell phone. You're going to add potential energy to it, and there's going to be a change in there's going to be a force or a work applied over a distance. While that movement is taking place, there's a change in potential energy, but then once it's stationary, it's then sitting at that potential energy. In this case, we're only, if you think about it another way, we're only changing the potential energy, but once it's stationary, it's just, again, sitting exactly where it is. Another way you can think about it is if you shove your hand in some water, I'm going to draw a really bad hand again, and there's going to be, that water is going to be displaced momentarily, and then, but then once you leave it in there for a second, the water then becomes stationary. It fixes itself and becomes where it's supposed to be, in alignment with your hand in the water. Then you take it out, there's a displacement again in the kind of reverse direction, and then it sits again. Similarly, this is what the electrons are doing. They're moving around to reorient themselves to the changing magnetic field lines, then they sit there. And then there's no EMF created, there's no induced current, and then once you pull it out again, there'll be another current in the opposite direction, and it'll again recenter itself and just sit like normal. Anyways, I hope these two kind of different explanations might help you. That's basically what Faraday's law is. There'll be a future video on Lenz's law, which is kind of the opposite of Faraday's law, or the other side of the coin, the way I put it. I hope you watch that video too, because it might help you understand Faraday's law. Anyways, thank you for your time, and I hope you enjoyed the video.